Okay, thank you to the organizers at first for letting me give a talk about IceCube and neutrinos in the multi-messenger context. So I'm gonna go through a few aspects of the IceCube real-time program related to the science that we do, but also how do we do it, which kind of infrastructure we use. So by now you should be familiar with this picture a lot. But why we are interested in neutrinos? Because of course they're formidable messengers. They are able to probe the densest environments. They travel undeflected. They carry signature of hadronic interactions, and they are not deflected as gamma rays. They're not absorbed. They're not absorbed as gamma rays. They're not deflected as cosmic rays. So they point directly back to the source. And so since a few years now, neutrinos are a big part of multi-messenger astronomy. And the way we detect neutrinos at the astrophysical energies is by using large detectors. In this case, I'm talking about IceCube. IceCube is an array of photomultiplier submerged in the Antarctic ice that detect the Cherenkov light induced by secondary particles resulting from neutrino interactions. And there is a large infrastructure that allows IceCube to relay the data in real time to the north and perform some kind of astrophysical selections, then produce the alerts that you can see on the platforms such as GCN. Just to have a reminder of what kind of event signatures we see in IceCube. So we have mu neutrinos that produce tracks. And since they leave this long signature inside the detector volume, they are allowed to be reconstructed with a resolution that goes between 0.1 and 1 degree on average. And they're the ideal channel if you're looking for point sources. Then we have cascades from Hall flavor interactions and charge current electron-neutrino interactions that have somewhat worse resolution than tracks because they are not that developed along one dimension, but still allow median 10-degree resolution and also a very good energy resolution. So cascades are invaluable if you do studies on the diffuse flux, but also, as you may have heard about the neutrinos from the galactic plane, they allow you to probe for extended sources. And now they are also starting to be integrated in normal point source searches. And finally, worth mentioning the double bang expected by high energy tau neutrinos, although these are very rare and too rare for astronomy. So I will not cover this event. Actually, I will mostly focus on tracks. So also to give you a bit of perspective of what you're looking at in IceCube, this kind of search has a huge background. That means that you are looking for more or less 200 cosmic neutrinos on top of 140,000 background events in a year. So you need to be very aggressive in trying to find a signal in this haystack of background. And you usually do this either by spatial clustering or finding spatial and temporal coincidence with astrophysical messengers. And this is what I will talk about today. IceCube, notably, has a long history of real-time time domain astronomy. Because if you see, basically, since the early years of the completion of the detector, he had in place already programs for the multiplet search. So you search for multiplets in the neutrino data in order to trigger mostly private alerts that are then followed up by partner observatories such ICTs. But since a few years, we also have a public neutrino program, alert program, where we release mostly tracks, but also cascades, that on an individual basis, they have a moderate to high probability of being astrophysical, and they're worth electromagnetic and multi-messenger follow-ups. Since a few years, we also have in place what we call fast response analysis, that is the follow-up with IceCube data to external trigger. But I will mostly cover the alerts that you may be interested in following up on an individual basis. And these are mostly the IceCube AstroTrack alerts. So this is more or less how it looks like into our detector, neutrino and astrophysical energies. Most of the time you are above 100 TeV. And these alerts are divided into two categories depending on their signalness, which is the probability of being signal over the number of, let's say the probability for that individual event of being a signal rather than background. And so we have two alert streams. The bronze that has on average 30 to 50% signalness, and the gold alert sample that has on average above 50% signalness. And these alerts are promptly disseminated via GCN network. So it's worth mentioning that it's this program that led to the remarkable association between a very high energy neutrino coincidence with the flaring blazar, the famous Texas source, that led to one of the most massive follow-up campaign with the detection of a flare in Fermilab, but also very high energy detection by MAGIC. You have heard many times about this. I will not go into details. It's just to give you an idea of what you can achieve with a real-time program. So what happens when we select, when our pipeline selects an event as an AstroTrack alert? So you usually have a prompt alert distribution within 1 minute that results in the production of a GCN notice that carries the event date, the time, the estimate energy, the FAR, and the preliminary reconstruction. After, on average, a few hours, you will also receive, in the form of a GCN circular, a detailed reconstruction carrying a rectangular region bounding the 90% containment contour of the event, plus comments on the specific events, and most notably, we report conventionally the associated 4 FGL sources, so the Fermi sources that are inside the contour. This has been mostly traditional. Doesn't mean that you should only look at gamma ray sources, is what IceCube has been doing traditionally. But yeah, there is no reason specifically to only look in the gamma ray domain, of course. An interesting thing that occurred in the course of the last year is that we had the publication of the first catalog of alert tracks. So if you remember my timeline I showed before, it's been a few years that IceCube has in place this real-time program, although the alert selection can be applied retroactively on the full data set of IceCube, and then we can look which events would have passed the alert selections if the program was in place at that time. And with this, you have a sample of a bit more than 250 events. That from which here you can see how they are distributed on the sky. You can see they're kind of clustered around the horizon because it's where the detector has the best acceptance. And this has been a public release that you can find on the Harvard Dataverse. And you can do all kinds of studies. Also, it can be a nice benchmark if you want to design a coincidence search, because you know what you will expect in the next 10 years of alerts from IceCube. And also has been now introduced also in Astro-COLIBRI, so you can find these events in on the platform. So I would go now a bit into the angular uncertainty, because it's something that is often not well understood, possibly also because of IceCube fault, I have to say. I mentioned you have a preliminary reconstruction and a detailed reconstruction. So the one you receive in the GCN notice is a simplified and faster variant of the reconstruction we use in normal point source searches. So the one we use for the offline datasets. These may not provide, it's very good on a statistical basis, especially if you apply them a bit more powerful variant. But may not provide very good information on the individual high energy events, because it doesn't account for the stochastic energy losses the particle has inside the detector. So this assumes that you have a nice infinite track with uniform distribution of light around the trajectory, which is not most of the time the case for high energy events like the one that produce alerts. So that's why we run a detailed reconstruction. It's a more sophisticated algorithm that accounts for the stochastic energy losses along the track. And we use a so-called skyscan method. Since this construction is a bit sophisticated, doesn't always converge if you try to fit the direction. So basically, we fix the direction on a grid of points in the sky, and then we evaluate the likelihood by fitting the other parameters of the event. And so we can also define the error contours in terms of likelihood critical values to produce our 90% and 50% containment regions. And this is what more or less you get out of it. You get this kind of likelihood landscape for the individual event. And we mark we have the 50 and 90% containment regions. And in fact, we do this by evaluating a likelihood function for the photon arrival times on a Hilpix grid. And to reduce the amount of pixel we have to test, the algorithm starts on a coarse grid, and then iteratively refines the patch of the sky where the highest likelihood is found. And to give you an idea, one event requires the evaluation on about 30,000 pixels, but also depending on how you set up your reconstruction. But there is margin for improvement. The main problem we have now with this system is that the current directional reconstruction has some limitations due to the impact of systematic uncertainty about how do we know the light propagation in the ice. So the coverage of the contours can be improved, as it's been already shown in some contribution by IceCube. But also, as of last ICRC, we presented new different algorithms that are being evaluated to improve the reconstruction performance and make it a bit more robust against systematic uncertainties. And the aim will be to release these individual event likelihood maps and contour shapes also in real time, because now what you receive is the bounded rectangle of the 90% area. And to do this, we have, to test this new reconstruction, we have implemented also a new generation infrastructure for the skyscan method, where we handle a parallelized workflow, where we distribute all the reconstruction of the pixels to a number of nodes that goes between 100 and 1,000, using as a backend a arbitrary queue, message queue. And then we access the reconstruction infrastructure with a very convenient REST API. That means you can send your data and retrieve your data through HTTP request. And this is handled by the SkyDriver event workflow management system that orchestrates the entire distributed computing for this reconstruction. And this allows us to have multiple reconstruction algorithms possibly going in parallel, and develop and test and develop improvements to the real-time RICO. All this new system is orchestrated with the SkyMist framework, which is a Python framework that interfaces with all the modules we have now, and basically processes the real-time events and automatically schedules the reconstructions using the SkyDriver event management system. And the idea that we developed SkyMist with is to standardize data formats and workflows that are part of the real-time infrastructure of IceCube that will allow us to disseminate the results and stick to the fair data principles, because somewhat we centralize all the formats and workflow definitions in, let's say, a single source of truth. And an idea that is being implemented using the Astro-COLIBRI API to automate the search of associated sources at the time and the location of the alert. And while this is quite an internal system for IceCube that doesn't have much importance if you're just a consumer of alerts, I think this represents also a nice new paradigm in which you try to hide the complexity of distributed computing from the user and provide a convenient interface to access the physics reconstructions for the individual events. So as a summary, the IceCube real-time system has been in operation since 2019. Enabled tens of multi-messenger follow-ups of IceCube neutrinos. Improvements are ongoing to improve the alert directional reconstruction. And these efforts are supported by a new generation infrastructure for the management of parallel reconstruction workflows. And a standardization of the data formats and workflow will enable a more timely and comprehensive dissemination of alert information to the community. So what you can expect in the few months time scale is, maybe that's a bit optimistic, but yeah, you can expect an improved reconstruction for real-time events and the publication in real time of the sky maps for the likelihood landscape of the individual neutrino events. Thank you.